Welcome to Module 1, Part 2. In this module, we are going to review closed process covered in Chapter 5 of your textbook and also go to Chapter 3 to review the PG model. The prereq for this module is Part 0 of Module 1, where we discuss the governing equations for a generic system. So we'll begin by customizing those equations for a closed process and go over the meaning of internally reversible process, the PG model, and various constant processes. Finally, on a separate section, we're going to do a complete solution, manual solution, and verify that using test calc. So let's begin by taking a look at a system which is closed. Closed means no mass transfer. As you can recall, there is heat and work transfer of all kinds. Of course, remember that external work transfer is given by boundary work, shaft work, and electrical work. These are the rates in kilowatt in the generic governing equation. Now, look at the mass, energy, and entropy equations. So if the system is closed, the mass terms goes out, so there's a big simplification. So in other words, there is no transport of energy, no transport of entropy. And the mass equation becomes really simple. dm dt equals 0, which means m equal constant. So for closed process, we don't worry about the mass equation. Mass is constant. Notice that the energy and entropy equation becomes simpler too, and so these are the unsteady equations for a closed system. Let's see how we can simplify this equation further. For that, we'll be considering what a process is. A process means an unsteady system goes from a given beginning state to a final state. It goes from one state to another state. So that the details in between do not remain important. So let's see how this governing equations, energy and entropy, simplifies. If you multiply both sides of the equation by time dt, then we get dE equals q dot dt. Okay, so the unit becomes kilowatt times second, kilojoules. Now, if we integrate this equation from a beginning state to a final state, what we get is here EF minus EB, which is the change in energy. This is called delta E, the change in stored energy of a system. And what is this? The heat transfer over the period of the process, Q dot times T. So therefore, it becomes Q, the total amount of heat that is transferred during the process. Similarly, the work, this is the rate of work transfer times time. So the dot goes away, and this is what we are left with. So this is the energy equation for a closed process. Recall that E equals KE plus PE plus EU. And if delta KE and delta PE are negligible, that is, change in kinetic and potential energy are not high, then delta E become equals delta EU equals Q minus W external, where W external equals W shaft, W electricity, and W boundary. A note about the boundary work, because we'll encounter boundary work a number of times while analyzing closed processes. Boundary work is given by integral PdV from the beginning of the process to the finish of the final state of the process. So to find the boundary work, the easiest way is to draw a PV diagram And suppose I have a gas in a piston cylinder assembly, and we find that a gas expands, and let's say the pressure decreases or something. We don't know. It depends on the specific process. Then the area underneath this graph, PdV, this is my B state. So this is the volume corresponding to B, and this is the volume corresponding to F. So this area is the boundary work, PdV. So this is the graphical meaning of that. If the graph looks simple, like a rectangle, suppose for a constant pressure process, then it's really easy to calculate the boundary work. We'll come back to this once we discuss the PG model. Now, how does the entropy equation simplifies? If you recall, this is the entropy equation for any unsteady closed process. Again, we multiplied by dt, getting rid of the time rate term. And now when we integrate from the start of the process to the end of the process, we get SF minus SB, which is delta S of the system. And that equals, if boundary temperature doesn't change during the process, you can write that as Q by TB. And this is the rate of entropy generation times dt. So the rate goes away. This is the total entropy generation. And the unit will be Q has the unit of kilojoule, Kelvin. So this is our entropy equation. And we have already derived the energy equation, and the mass equation is very trivial. Mass remains constant. Just to interpret these terms physically, here is a couple of images from an animation 5A flow diagram. Look, notice if this is my system, the red dashed line showing the boundary of the system, then the energy equation delta E equals Q minus W external is intuitively understandable. This bubble inside shows delta E. If more heat goes in, then the work comes out, then of course delta E is going to be higher and higher. One note to remember, don't forget the Wien-Heap convention, which means that whenever in this equation Q and W external are algebraic, so when you substitute, if heat in is positive, heat goes into the system, the diagram is in the direction of the positive heat, Q will be positive, and if external work is coming out, it will be positive. WIN means work in is negative, heat in positive. So work comes out means work is positive. So depending on a particular case, we will figure out the sign of W external and Q and plug them in here to find delta E. Also remember, delta E is approximately equal delta U. Almost most of the time we will use this because the change in KE and PE are mostly negligible. The entropy equation likewise shows how the entropy of the system changes. First, entropy can enter because entropy travels with heat. If the boundary temperature is TB, then this is the entropy that is going into the system with heat. And entropy can be generated. This term shows entropy generation, these guys, because of friction. So because of the two reasons, Q over TB and entropy generation, the entropy of the system changes. So delta S, the change in the system entropy, equals the entropy that comes in by heat plus entropy that's generated. So this equation can be now physically understood. As much as possible, we will employ the physical meaning. The change in energy equals heat that comes in minus work that goes out. The net gain by the system is delta E. The change in entropy, the net gain of entropy by the system, is because of entropy coming in by heat and entropy that can be generated during the process. It should be noted that the external work is mostly boundary work. And the boundary work in heat transfer Q can be related to a TS and a PV diagram very nicely if we remember that boundary work is given by integral PdV. And to find out a meaning for heat transfer. Let's write the entropy equation for a closed system again. And as we did before, multiplying by dt, ds equals dt times q dot, sorry, this is q dot, over tv plus s dot gen dt. And now suppose the system is internally reversible, which means there is no friction. Suppose there is no friction inside. That is an ideal system, ideal process. Then you can see that if a system's temperature Tb changes, if I have a system whose temperature is changing, okay, let's go to this plot. Suppose I have a system whose temperature is changing as the system is getting heated and work is getting done in a process. Then the equation that we just wrote, we can simplify this as ds dq by T, whereas dq is the heat that is transferred in this time dt, which simplifies to dq equals TdS or q equal integral TdS. And this is what is shown in this plot, in this animation. You can go and visit this animation that goes over this more thoroughly, or in your textbook. That in a closed process, if you can draw the TS diagram or the PV diagram, then the area as the system goes from a beginning state to finish state, forget about what the graph looks like. Suppose some kind of plot will show how the system moves from B state to F state. Then the area underneath the TS diagram plays an important role. You can see that it is proportional to the heat transfer. So because the heat transfer is T d capital S, which is mass time T small ds B to F. And in the T and small s diagram, TS diagram, this area is proportional to the heat transfer. Just like in a PV diagram, this area is proportional to heat, the work transfer. So as a result, these equations, the meaning of these diagrams will play a very important role in all our future development. So to summarize, in a TS diagram, the area underneath is proportional to the heat transfer. In a PV diagram, the area underneath is proportional to external work transfer. Okay, now let's go over the PG model in a very succinct manner. The PG and IG model are basically models with which we can find properties of a gas. The PG stands for perfect gas model and IG stands for ideal gas model. In both PG and IG model, they are both based on the first assumption is that the ideal gas equation of state is valid. It has many different forms, but PV equals RT is one of the best form to use for mechanical engineers, where P is the pressure in kilopascal, absolute pressure, V is the specific volume, R is the gas constant, 0.287 for air, very handy formula, and T is in Kelvin. So if I have a piston cylinder device, you know the pressure and temperature, you can and you can easily find the mass of the air because specific volume equals volume by mass. So therefore, if we substitute that, you can get the formula P V equal MRT as an offshoot of this. So if I have a box, a rigid box, and we have some gas inside, suppose we have some air inside, if you know the pressure, suppose the pressure is 200 kPa, temperature is 300 Kelvin, and then you can find the mass, and suppose the volume is 2 meter cube, you can very easily find the mass So you got to make sure you know how to find the mass of air or mass of any gas using the ideal gas equation of state. So this is an equation that's obeyed by both PG model and IG model. But the simplification for the IG model, PG model, is that we can get very simple formula for change in internal energy. Specific internal energy is given by CV times T2 minus T1. In other words, it's delta U equals CV delta T, and delta H similarly is CP delta T. The CP value and CV value for air should be listed, should be almost memorized, because we are going to use that a lot. But you can go and find that if you go to test property tables, and if you go to the PG model common gases, you can find the air values. Molar mass is about 29, 0.287 is R, CP is 1.005, and CV is 0.718. And the value of K, the ratio of CP and CV, is 1.4 for air. Again, these are very handy number to remember. So CP equal 1.005, CV equals 0.718, same unit, and K is CP divided by CV equal 1.4. So notice that CP is greater than CV always for a gas. So this is our PG model. For IG model, ideal gas model, CP and CV are not constant. They are function of temperature. So therefore, ideal gas model becomes more complicated. To find delta U or delta H, you have to consult a table, and that table may not be available for many gases. So we are going to stick to the PG model, even though you'll be tempted to sometime use the ideal gas table, thinking it's simpler to use. Actually, the PG model gives you much better insight. If you have a formula, you know immediately that delta U is proportional to change in temperature. If you look at a table, that meaning doesn't become obvious. So we are going to stick to the PG model in all our future work. Whenever you see a gas, blindly use the PG model and you'll not go wrong. So how do we express change in entropy for a perfect gas? The formula is again right here. Delta S is given by Cp ln T2 over T1 R P2 over P1. We already know the value of Cp and R for air. So delta S can be found. But more importantly, there are two different formulas for delta S based on what ratios you know. But probably the more important formula here is what happens if entropy remains constant. We'll soon come across various processes where entropy remains constant. If we substitute delta S equals 0, we get relationship between pressure ratio, temperature ratio, density ratio, etc. in terms of K. So, for instance, if we just know the volume ratio, we can figure out the temperature ratio. So we are going to use this kind of relationship known as the isentropic relationship, or equation 11 in table J, quite a bit. So in the future, when you make reference to isentropic relationship, you'll find that if we know the temperature ratio, we can find the pressure ratio. If we know the pressure ratio, we can find the temperature ratio, etc. All from a single number K. K is the specific heat ratio, Cp over Cv, which is 1.4 for air. So to summarize, the isentropic relationship we are going to use if entropy equal constant in a process, and we'll try to figure out in what kind of process entropy remains constant. Then T2 over T1, P2 over P1 V2 over V1 or specific volume over V1, etc. are related by equation 11 of table J. We call it table J, where in that table we have listed all the relevant equations we are going to use. Okay, now it's time to go look at specific processes and put those into practice. So let's do a TS diagram and try to think how, let's say, a constant pressure line will look on a TS diagram. So before we go for this particular process, let's quickly make sure we understand how to draw a constant volume line on a TS diagram. So we have a gas and a TS diagram. Suppose, at a constant volume, we are heating the gas as shown here. This piston is stopped from moving through this stop, so we are heating the gas. So as you can understand, as we heat, the pressure will increase because the gas is not allowed to expand. So why does the TS diagram, the line, how should it look? So suppose in the beginning, we have a state here. This is my B state. Now as I heat the gas, obviously the temperature will increase. It's obvious. And we can also think of entropy to increase, right? Because as we know, as we add heat, we are adding entropy at the rate of Q dot over TV. Entropy goes in, right? Every time heat is added, entropy is added. And even if there is no friction inside, the entropy cannot go anywhere because there is no mass transfer and there is no other mechanism. If there is friction, even more entropy will be generated. So entropy will increase. As a result, the plot kind of goes this way. Now, how do we figure out exactly how the plot moves? It's really like this. To understand that, think of what the slope should be. And if you recall the TdS equation, that's an equation that is very important, fundamental equation from your ME 350. TdS equal du plus TdS equals du plus PdV. So if we have a constant volume, this is always true for not only for gas, this equation is valid for any material, any pure substance. So it means that if there is a little change in the system's equilibrium, the change in entropy times temperature is related to change in internal energy and change in specific volume. Now, this is a constant volume line, so volume doesn't change along the line. And we want to know how this line looks. So dV equals 0 because volume remains constant. And we also know du is given by Cv dt. That's why delta U equals Cv times delta T, if you recall the formula. So TdS equals Cv times dt, right? So therefore, dt over ds, and that's the slope, right? Look up that. This is dt and this is ds, right? So the slope is dt over ds is given by T over Cv. So in other words, this equation tells you that the slope, as the temperature increases, the slope increases. And that explains why the graph becomes steeper and steeper as you go out to the right. And it's divided by Cv. In other words, Cv is a constant. So anyway, so you understand that the slope goes like this. So this is how a constant volume line looks like. Coming back to this process, so if you're heating a gas, it will go from, let's say, state 1 to state 2 along this line. And as you recall, the area underneath will be proportional to the heat transfer. That's from our understanding of internally reversible process. Of course, there is no work transfer because the system is boundary is not moving. So therefore, there is no change in volume. Boundary work is 0. So if we apply the energy equation to this system, it's really simple. Delta E equals Q minus W external, which is WB mostly. Sorry, not Q dot Q. There is no boundary work. So therefore, Q equals delta E equals delta U equals M times delta small u equals M CV times delta T. So the the heat transfer can be calculated if we know the temperature change of the gas. So it's very simple equation. Q equals mCV delta T. So if I know the CV of air, for instance, which we already know 0.718, and if I just know the temperature change multiplied by the mass of the gas, that is the heat transfer. Let's now take a look at how a constant pressure line will look on a TS diagram, because this is a constant pressure process. How can you keep the pressure constant? We put whatever weight we want here to get a particular pressure. And now if we heat the gas, as you can understand, the piston is free to move. So the pressure inside is determined by the free body diagram of the piston. The downward force and upward force must be equal. So upward force is pressure times area, that is pushing the piston up. And the downward force is what? The weight of the mass on the piston and the atmospheric air, which is pushing it down. So if you do a free body diagram, we'll get PA pushing it up, mg, I'm dividing by 1000, plus atmospheric pressure times A. So this equation will tell you what is the pressure inside. As a matter of fact, by changing the mass of the weight, you can change the pressure inside. But once you have a pressure inside, now if I heat, our natural tendency will be to say, oh, the pressure will go up. Not really. The moment the pressure goes up inside, the downward force is not changing. So therefore, if pressure increases, the upward force will be higher than downward force, and the piston will accelerate up. So as soon as the pistons start moving, though, the pressure will try to go down. So the pressure inside will be controlled by this downward force, which is never changing. And that's why the pressure inside doesn't change when you heat a gas and the piston is free to move. So again, there is plenty of animation in chapter 0 to explain the free body diagram and why the pressure doesn't change, but you've got to understand, as soon as you see the boundary is free to move, that means the pressure remains constant. So how does a constant pressure line look on a TS diagram? Again, if we start with our TDS relationship that we did before, this is also a famous TDS relationship. We start with this one because if pressure remains constant, this goes to 0. So therefore, TDS, which is dH with Cp times dt, and dt over ds, which is the slope of the line. Suppose the slope of the line, as we can see, as the system goes from say state 1 to state 2, dt over ds is given by T over Cp. Again, just like the constant volume line, we see as the temperature increases, the slope must increase. So the line must slope upward. However, it's moderated by Cp. You divide by Cp. Recall that this is the constant pressure line, and that was the constant volume line, which was T over Cv. And Cv is always smaller than Cp. So therefore, the slope for a constant volume line is greater than the slope. So this is greater than the slope for constant pressure line. So this will come very handy in the future. So just to remember that the constant pressure and constant volume line, to summarize, both trend upwards. But if this is constant pressure line, then the constant volume line will be steeper, as indicated by the slope here, because Cv is smaller than Cp. Okay, now we want to get an expression for, let's say, in this case, there will be heat transfer and work transfer both. So let's get an expression for that. Well, the energy equation will give us delta E becomes delta U. We'll routinely neglect kinetic and potential energy. Delta U equals Q minus WB. But in this case, there is both heat and work transfer. Well, but one thing for sure, the boundary work is really easy to find, because if you draw a PV diagram, it's constant, right? So therefore, if you go from state 1 to 2, this is my boundary work. So we can write so this is the boundary work we're substituting. So this area P V2 minus V1, which is the boundary work, as you can see, if V2 is bigger than V1, then boundary work is positive, so everything is perfect. Now we can simplify that. We can say, okay, therefore Q will be equal, delta U will be what? U2 minus U1 plus P V2 minus V1. Nothing wrong. So we can figure this out, because U2 minus U1 can be found, V2 minus V1 can be found, and pressure remains constant. So therefore Q and W boundary or W external has been determined. But wait, we can simplify this formula to a handy formula. Look, we can write this as, if you want, U2 plus PV2 minus U1 plus PV1. And we know pressure remains constant, so we can write U2 plus P2V2 minus U1 plus P1V1. Well, if we take mass common, we can write U2 plus P2V2. And if you recall, U plus PV is what? Enthalpy. So you got a very simple formula for Q. When pressure remains constant, the heat transfer is given by enthalpy difference times the mass of the system. So again, we will encounter constant pressure process, constant volume process when we analyze IC engines soon. And finally, let's go over the constant entropy process. That's the last process we'll describe before we go to some problem solving. Well, a constant entropy process in a TS diagram is very simple, right? Entropy doesn't change, so it'll go along up and down. Now, what is a constant entropy process? First of all, suppose I have a process where, let's say I'm compressing a gas and it's insulated. There is no heat transfer. So if we write the equation for that, delta S equals Q over TB plus Sgen, we know the change in entropy depends on how much entropy is transferred due to heat and how much entropy is generated because of friction. If there is no heat transferred, like the system is very well insulated, this goes to 0. And if there is no friction, this goes to 0. So adiabatic plus no friction. Another word for no friction is reversible, right? Makes the process isentropic. Well, sometimes the process is so fast. Suppose you're compressing a gas so rapidly, even if the cylinder is not insulated, there is no time for heat transfer. And the adiabatic assumption may be really good one. So in a car engine, the gas is rammed into compression so fast that even though there is no insulation, the adiabatic assumption is perfect. And no friction is also a good idea, because we are not talking about the friction between the cylinder and piston. It's the friction inside the gas. When a gas is compressed or the gas expands, what happens is that throughout the gas, changes takes place at the same time. So there is not much difference between point to point. And when there is no difference between point to point, there is less friction. So no friction is also a good assumption in this kind of situation. So it turns out whenever you see a gas expanding very quickly or contracting very quickly, then entropy remains constant. For the energy equation, delta E equals Q minus W external, again, will reduce to, because Q equals 0, it produces very simple formula for boundary work, mCV delta T, and W external is mostly W boundary. And so this is how we'll find the boundary work for an isentropic process. Integrating PDV will be much more difficult because, as you can see, the PV diagram is not simple. Suppose in this case of compression, we are putting weight on the piston, and as the weight is increased, the piston keeps going down and the pressure keeps increasing. So the beginning state is here, the final state is here. The volume is decreasing and the pressure is increasing. And so the area underneath is definitely equals WB, but that's much harder to find by integrating this equation than by knowing how much the temperature changes and then multiplying by mCV. So again, I've covered a lot of theory here from chapter 5. Go and review that chapter and go over this lecture, at least different constant property processes that we have discussed and the governing equation, mass and energy, before you go and check out the problem that I have covered in the solution part. And we'll cover two problems, one constant pressure process, another will be a constant volume process. And they will become very useful as we do internal combustion engines.